Dang. Oh, hi. I'm Michael Fudge, just out here practicing my golf game. Let's not putter around any further and get to the whole lesson.
All right, it's time to take a look at the physical model, performance, and how we can improve performance through indexing. So we'll start out with our agenda as we always do. What is the physical model? What are the details of the physical model in Microsoft SQL Server? And we'll focus on file groups, and pages. We'll talk about indexing, and we'll start with clustered and non-clustered indexes. We'll also move on to understanding query plans, that is, figuring out how to improve a query by looking at its query plan. How you can address fragmentation in your indexes and correct it. Then we'll take a deep dive into Columnstore indexes and ways that you can index views, not queries, but views. Let's start and look at the physical data model first. So the physical data model is an implementation of the logical model. It is dependent on an implementation. The physical data model for Microsoft SQL Server is different than the physical data model for MySQL. Every DBMS has a different physical model. Now they're very similar, but this is what makes one product different from the other, and this is why there's so many of them out there. So the physical model is concerned with performance and how things are physically stored into files on the operating system, files on disk on the operating system, and it's part of the DBMS architecture. And when you want to improve performance, you have to take into consideration the DBMS architecture of your chosen DBMS, whether that's SQL Server, MySQL, Oracle, whatever. You are constrained by the features of that particular product that you have selected. So as we recall the 5 different representations of a database, we have that conceptual model, logical model, right? And then way down at the bottom, we have the physical model. And this is how that internal model and that external model are stored within the DBMS and within the respective operating system. So if you're thinking about the DBLC, while most of what we look at in the physical model is in maintenance, you should also consider physical design while you're in the design phase and the implementation phase. It really is something that should be considered all along. And why do I mention that? I mention that because you might have a large volume of data that you are planning to put in there at the initial rollout, and you may need to think about performance around that large quantity of data. Most of the time in maintenance, we might look to tune the physical model that we have built in implementation, and that's where commonly the physical model comes into play in the maintenance phase. All right, so let's talk physical database design. Some people will argue that it does not matter. Physical database design is something that you can safely ignore, and if you have performance issues, you can just throw better hardware at it. You can just buy more cycles in the cloud or improve the implementation by upgrading and paying more for the services you're using in the cloud. My argument is that physical database design matters if you care about performance. You can only pay your way out of a performance problem for so long. That is, you can only upgrade your hardware for so long before you hit a limit there, and then once again you now have to care about performance. So why not just care about performance from the get-go? That is my mantra, and that's the way I have always thought about database management systems and implementations. Okay, since that physical data model is dependent on a DBMS, we should probably look at the physical data model for Microsoft SQL Server, which is the DBMS that we are using. Now, your mileage may vary between one DBMS and another, but remember, they all have a similar layer of abstraction around them physically. Ultimately, what you store in a table, or when you create a table and then you store data in it, that's got to be stored in a file on the operating system somewhere. That's just how an operating system works. So how each DBMS chooses to abstract that away, that's going to vary DBMS to DBMS, but fundamentally they're all doing the same thing. Okay, that's the one caveat I have about, well, I did pick Microsoft SQL Server, but yes, there's some commonalities among all of them. So at the highest level is the server, and this is the product installed on an operating system, and this could be in a virtual machine, it could be on bare metal, or it can be in a container. So in the class, when you're doing your labs, you're actually running the server within a container, but it really doesn't matter which way you're doing it. This is the highest endpoint in the abstraction, is a installed version of the DBMS. Now, once you have one installed version, you can opt to install multiple copies of that same version on the same server. And why might you do this? Well, in the open source world, you would probably never do this. But in the world where you pay money to license a product like Oracle or Microsoft SQL Server or IBM DB2, you might not be in the business of buying 3 copies of it so that you can run a test environment, a development environment, and a production environment, which most organizations will run these 3 environments. The development environment is for adding new features. The test environment is for introducing those new features to a set of users. And the production environment is, as you would think, it's the one that runs the real production version of the application that runs on the database. So if it costs X amount of dollars to license Microsoft SQL Server, one way you can get around X times 3 for each of your environments is to run one server and then split that server up into 3 installed instances. Okay, so a lot of DBMSs that are licensed this way have the ability to support multiple instances. Then the next layer down from an instance, you know this, it's a database. So you have used the Azure Data Studio application to connect to your DBMS with Microsoft SQL Server. And in there, we've had several databases. We've had TinyU and Demo and Payroll and FudgeMart and FudgeFlix and all these other databases. And what you want to know about a database is the database itself is physically stored as one or more files. At minimum, it will have a file called database .mdf. So if the name of the database is payroll, it's payroll.mdf. And if you have the database set up in its default mode where it uses a transaction log to hold every single change made to the database, then that would be named, payroll_log.ndf or .ldf, payroll_log.ldf. You can also add additional database files to the database, and there's going to be a variety of reasons that you might do this, and we will talk about them in due time. But one of the main reasons why you would add other files is so that every single table that you're inserting into isn't all writing to the same file. Imagine you take each table and put each table in its own file, right? That spreads out the I/O among each different files. Furthermore, you could take the tables that you write to a lot and put those files on better performing disk, right? So you might spend a lot of money on some really fast disk, but you can't afford to put everything on that fast disk because it costs a lot in storage. So you might take the tables that get a lot of action and store those files on that disk and then store the other files on the other disk. And then you have to, when you create the tables or alter the tables, tell them where they go. And we're going to talk about that in a bit. So where they go is called a file group or a table space. Other DBMSs call them table spaces, but in Microsoft SQL Server, they're called file groups. And a file group is a logical name for one or more physical files. So when you create a database, it makes a file group called primary, and it puts the database file in the primary file group. So when you say create, table employees, that employees table is created in the primary file group, and then that lands in the database file. If you wanted it to land in another file, you would create a file, you'd create a file group, you'd add the file to the file group. Then when you made the table, you'd tell it to not go into the primary file group by default, but again, select a different file group. We will demo this. At the smallest level in the Microsoft SQL Server DBMS, and this is very common for every DBMS, is the page. And the page is how we retrieve actual data inside the file. And the way it works is we don't go right down to the row level and retrieve that data. We retrieve them in chunks, and those chunks are called pages. So you might have a very large table, and that table is broken up maybe into 100 pages. And if you want to retrieve a row, it's inside a page, and that entire page is pulled into memory. So it's just a kind of a performance thing. Rather than pulling out the one row into memory, that's too granular. We pull the entire page out into memory. And these are all abstracted away from you. But it's good to understand how they work in order to figure out how you want to improve the performance of your database. If you want to improve performance, you have to have a little bit of an understanding of the physical model. It's just that way. So let's visualize the physical model. We have the hardware, the virtual machine, or the container. And then inside that, we have the server. And these are both physical boundaries. They're real things. Then we have the instance, which is another physical boundary. So in this example, I have two instances. I have the default instance and some other instance, which I didn't name in this example. And then inside the instance, we have one or more databases, and this is a logical boundary. And then the database consists of a file group, which is another logical boundary. And then inside the file group is a physical boundary, a file. And then within the file, we have pages. And these pages represent physical chunks of the file. And the page is of a fixed size and owned by various objects like your tables, your indexes, your views, all that stuff. And it is the smallest physical unit in the DBMS, is the page. All right, what is a page exactly? Let's dive into this a little deeper. In the DBMS, we have rows or written physical blocks inside a file called pages. These pages are 8 KB, 8 kilobytes, 8,000 characters, if you like to think about it, in size in Microsoft SQL Server. And this is the smallest unit of storage in the database. And the table boundary is the page. So I have a database payroll. I have a file group primary. It has a file payroll MDF. When I created the table employees and then inserted data into that table, all those employees might span 2 pages. I don't know how many pages they span. I didn't look. I'm just saying they might span 2 pages. And then the paychecks table, it's bigger. That might span, 7 pages. And it's because it's larger. And as we add more paychecks, they'll grow in size and use up more and more pages as we go. All right, let's talk about how data are inserted into pages. So this is physically how things get represented. Imagine each of these numbers here is a row, right? And this page, right, is an 8K page. So each of these rows would be about 2,000 characters. So if you think about what you're inserting into the table, that the space that they take up when you have int and varchar and decimal and all these other data types, in summary, each row takes up 2,000 characters. And so that's why there's 4 values on this page. That's all you can fit on this page. Now, in reality, you can usually fit a lot more than that on a page, but I'm trying to keep the visualization simple. So here we have 7 records. And these are IDs, right? So 1, 2, 5, 6, 7, 9, 10. These are IDs. And this is the boundary is a file, and that's here. And that's in some file group. We don't really care where it is, okay? And then we do an insert. We insert into this table value 9. I'm sorry, this should be an 8, this right here. Okay, so we insert into value 9, and then it just moves over, it moves over the value, and then we're done. Okay, and it didn't need to go on to another page, no big deal. So let's insert another value here, 3. When we insert a 3, it belongs on page 1, but there's no room on page 1. So what happens is we split the page at 3. So 1, 2, 3, and then 3, 5, and 6 go on a new page called page 3. And page 1 points to page 3, and then page 3 points to page 2. We don't rename the pages. Renaming the pages would take too long. So we save that for a separate operation later if we wanted to do that. So this is why I've been harping on you that we want to use surrogate keys for primary keys, because this will always guarantee that the pages don't get out of order, because the next one that you would insert would not be 9, it would be 11. And the next one you would insert after that would be 12. And then the original number would be 1, 2, 5, 6, 7, 9, 11, 12. And it would just use up pages going forward. When you insert data out of order like this, it makes the pages kind of get all scrambled. And then you have to constantly rebalance, if you will, the pages, or reindex the pages, as it's known. Okay, let's talk file groups. A file group is a logical name for one or more physical files. So it's logical storage. They cannot exist outside a database, so it's not like you can create a file group and then add the database to the file group. The file group exists within the database. Every SQL Server database has a default file group called primary. So when you say create table and you don't specify the file group, it goes in the primary file group. So you can alter your database and add a file group like this. And then if you want to view the file group, you can say select from sys file groups, and you can see the file groups within that database. Now, file groups aren't helpful without files. So a file group requires one or more physical files on disk, or else you won't be able to store the table in the file group. Right? Because if you go back to the diagram I had before, it was database, and then it was file group, and then it was file. So if I want to insert something into the, I want to create a table, it's got to be within a file group, and that file group at least has to have one file, or else it's not going to insert. Add the table. So a file group is a logical structure, whereas the file specifies where the data is actually stored. Every SQL Server database has a file name called database name.mdf. So if the database is demo, it's demo.mdf, and it's in the default file group primary. And you alter database, and then you can add a file, and then you can point to the name of the file and then the path to the file, and then you can say which file group it belongs to. And this is basically how you add a file to a file group. And then you might want to say, well, how do I see the file groups, right? So you can say select star from sys file groups. That's going to show you the file groups. Select star from sys database files. That's going to show you the files. If you want to see which file is associated with which file group, that requires a join. So you have to do a join like this. And we'll do a demo that shows how to do this join. But basically what you're doing is you're finding the object, you're finding the index name, and then you're finding the file group name, and you're retrieving all the objects. This shows you what objects are in the file group, by the way. So you can see which table is in which file group. And this U means user-created tables. My head's in the way. It means user-created tables, because you don't want to show what are called the system tables or the internal tables. All right, how about a demo? Let's do a demo. And in this demo, we will go into Azure Data Studio. I'm also going to hop out at one point to the command line and jump inside the Microsoft SQL Server container so I can show you the physical files where they exist. And then after we do that, we will add a file group and a file to the demo database, and then let's move an object to another file group. Okay, and let's see it all fold with physical files. So it's going to be a little switching around in this particular demo. Okay, I'm out here at Azure Data Studio, and I am looking at the demo database right now. And in the demo database, you'll see here's the demo database on my left. And then over here, I'm going to look at the files in the demo database. And I have two files. I have a rows file, which contains the data. And then I have a transaction log file, which contains the changes made to the data. And you can see where the physical file is located, because remember that every database has at least one file in it. So let's take a look at the file groups. Let's do select file groups. So the file group is the primary file group. So what you don't see is where are the files in the file group. You don't get to see that. You have to do a join. So you have to do something like this where you say everything from file groups, join sys database files on data space ID, right? So this data space ID. So sys file groups, data space ID equals sys database files, data space ID. And this will give you what we wanted, which is a combined look of the primary file group is this file right here, demo.mdf. Okay. Let's add a file group to demo. Let's do that. And what we're going to do is we'll just, I don't know, let's take these products tables here, FudgeMart products and Micazon products, and let's move them into the file that we're going to make, okay? And then show that they're in the file as part of the demo. So let's alter the database demo, and then let's add a file group. Let's call it products. Now, the file group names are case sensitive, and the convention is they should be all capitalized like this. Okay. Let's do that. Okay, and then let's run this again. Now you only see one row file group because we haven't associated the file group with a file. But if I just came down here and said select, everybody from sys file groups, you'll see that there's now two file groups. There's the primary file group, and then there's the products file group. But the products file group doesn't have a file yet, so I got to do that next. So let's alter the database again. Let's add a file. And the name of the file is going to be, so here's the properties that we need to add. The name of the file is going to be products data. It's going to hold data. And the file name, now you might be wondering, where do you save these files? This is important. So if I go back and look at this query, you'll see that we're saving these files in a path var opt mssql data demo mdf. So usually what I will do is I will copy this because I want all my data files to be in the same place, at least for now. And then I will go down here and I'll put that in there like this. And this time I don't want to call it demo. I want to call it products data. That's what I just want to call it. And I don't need anything else. And then I'm going to say, let's take that and add that to file group. And then it's called products. And we'll run this. Okay, and then we're going to go and run this one again. I'm going to bring it down here. Remember, this one here is going to show me which file groups and files are in this database. And now there's two. There is demo MDF and products data MDF. I should have called it NNDF instead of MDF, but it still works regardless. That's just the convention that should be used. And okay, so it's there. So now you might be wondering, all right, how do I see what objects are in which file group, right? So this, unfortunately, is a very large query. So I'm going to paste it in here and just explain it. This will show you what objects are in which file group. So you say, hey, select from sys objects, join that to sys file groups, join that to sys indexes, and then give me the user objects, and then give me the clustered index name, which represents the table, the file group, and then the object name. So this will tell me what table is in which file group. Okay, so all of them are in the primary file group, which makes sense because we didn't have the other file group until now. All right, so moving that file, moving this table here, let's try to move Micazon products to a different file group than primary. What you have to remember here is the clustered index is where the data is physically stored. So it's physically stored under this primary key. So I actually have to drop that clustered index and then recreate it. An easier way to do it is with actually the create statement. Now, clustered index is what we're putting on a primary key. You're going to learn more about indexing in a bit. So this is a little bit of cart before the horse, but I do want to show you how file groups work. So if I say create a clustered index, this is a way of making a primary key, and I'm going to give it the same name. Oh, that didn't work. It's right here. Copy that. So that's the same name as before, and we're going to make it on the Micazon products table. I got that right? I have no confidence that I can spell anything anymore. It's sad. So Micazon products. And then the primary key of this table was product ID, right? And then what I want to do is I want to add a thing that says with drop existing, which says, okay, make this new primary key by dropping the existing one. And then I want to say on, and then my new file group, which is called products. So hopefully this works. I haven't done one of these in a while. Oh, with drop existing like this. I got too many drop existings in there. All right, I got to, I think I got to say primary key here. Like that. Maybe? No. Yeah. Let me think about this for a minute. No. It's a unique. Remember, a primary key is a unique constraint. So I need to say unique clustered index. There we go. All right. So now I move that to a different file group, and I'll show you that. And now the Micazon products is in the products file group. So that every time I write to this table, Micazon products, it writes to a different file than when I write to flag colors, for example, because that's in a different physical file. And I guess we'll conclude the demo by showing you where the file is. Okay. So I'm out here at the command prompt. And I'm going to do a docker compose exec mssql bash. So let me explain this. So I'm going to execute a command on this container. And what I want to execute is the shell command, which brings me to a shell. So now I'm actually inside the container. I'm inside the operating system of the Microsoft SQL Server container. And if I go to the folder where the data is stored, I can see all the different MDF files there. So cd var opt MSSQL data. And if I just get a list of files with ls, let's do a LSL, you'll see I have, demo MDF, FudgeMart, right? Northwind. And if I go back to Azure Data Studio here, you'll see I have demo, FudgeMart, Northwind, right? And if I go back to the terminal again, you'll see down here I have products data, which is that file that I added. Now, some files are the same size, and then others are bigger. And the bigger files needed more space, right? This is the minimum size of every file that you make. And then if it needs more space, like it would with FudgeMart or FudgeFlix, it uses the additional space. So that's basically how the physical files work. If I wanted to improve performance of maybe payroll, what I might do is I might take the paychecks table, make a file, and put that file in a folder that has like faster disk than where this folder is. And that would help improve the I/O because the reads and writes off that disk would be more efficient. So in summary, that's basically files, file groups, and how you move a table from one file group to another. Basically, you're going to use this here. You're going to actually recreate that unique clustered index, which is really what a primary key is, the same way, and drop the existing one, and then just move it to the other file group. And that will take everything in that table and move it to the other file group. All right, time to talk about indexes. So the database index improves the searchability of our data at the expense of maintaining multiple versions of it. By default, every table needs to have at least one index, and that index governs how the data is physically written to the table. That is the clustered index. Just like the index in the back of a book takes us to a certain page where that word occurs, a database index takes you to a specific database page based on the key value that's referenced in the index. Okay, so the database will take you to the page based on whatever it is you're searching. The index was built around that key. So you can look through a database table linearly, a page at a time. That's called a scan. Or you can jump right to the correct page using the index. That is called a seek. Generally speaking, the seek is better than the scan because computationally we are jumping right to the right place and grabbing the right page. The scan is like a loop that says, are you the right page? No. Are you the right page? No. Are you the right page? No. Are you the right page? Yes. Then it stops. So it's a measure of performance, whether you go right there or you have to find where you need to go. Okay. So first up to bat here is the clustered index, and the clustered index sorts and stores our data in the order of the key. So when we create a table and we say primary key customer ID, then the table will be physically ordered by the values in the customer ID in ascending order by default. There can be only one clustered index per table since rows can only be stored in one order. They can't be physically stored in 3 different orders. And by default, the primary key contains a clustered index, but this is not a requirement. You can actually set a primary key and then set a different value to be the clustered index. Okay. And there are some use cases for doing that. The pages are organized by the clustered index. So, primary key is clustered index. This is basically why auto-incrementing values such as surrogate keys are great primary keys, because as clustered indexes, they avoid page fragmentation. So using int identity or using a timestamp is a good idea for your primary key, because those will always be increasing in value over time as rows are inserted. So if you can't use that, the ideal key in clustered index should be narrow. You don't want a big, wide, you don't want a varchar 100 to be a primary key. That's too wide. And what I mean by wide is that's too many bytes to search through to find out whether or not it's something you scanned for or seeked. It needs to be unique. It would prefer to be static. That is, you don't want to have an email address be primary key if that email address is going to change all the time. And if it could be naturally in ascending order or increasing order, that's even better. So let's visualize our clustered index again. I have a table, 4 rows in it. Then I go to insert grapes. Because the ID is the clustered index, I don't even specify it because it's an identity, and it just adds grapes and puts a 5 in there for the ID. And then I want to insert lemons, and then it just adds lemons, and it uses 6 for the ID. So this way, this method guarantees that we will always have nice clean pages, and the data will be added to the end. So we have page 1 here, and we have page 2 there, and page 3, the next thing that gets added, that drops onto page 3. And we don't have pages out of order or anything like that. Just works out nice and neat. Let's revisit the create table statement. So we know about create table and columns, and we know constraint PK and primary key, but now you can add clustered or non-clustered. The default is clustered. Okay? Clustered means you're going to use the primary key to physically store the data in that order. And then you can specify a file group for the primary key. And then you can specify another file group for the table itself. So you can have a separate file group for the primary key and a separate file group for the table. And the PK can be clustered or non-clustered, and you can use separate file groups for table and PK. And the table can only have one clustered index. You can't have 2 clustered index. So non-clustered index primary keys make sense for natural keys. If you don't specify a clustered index, the data is just inserted at the end. Okay, so it's naturally time-sensitive data as the data is physically put at the end of the table as it's inserted. Okay, so if I insert Mike and then I insert Dave, and then I insert Alan, they're stored in the file Mike, Dave, Alan, because that's the order in which they were added. Okay, basically how that's going to work. So how about another example? And in this example, what we will do is show you a non-clustered index, and then show you that you can only have one clustered index on a table, and kind of demonstrate that you can cluster natural keys could be non-clustered. And we'll go from there, okay? All right, I'm out here again at Azure Data Studio, and we're going to do a demo this time. What I'm going to do is I'm going to make a table called Other Products, because I already have a FudgeMart products and a Micazon products here. And putting the rows in it is really not going to matter, because what we want to focus on here are the clustered and non-clustered indexes that get created. Now, we've seen this. So, create table, other products. And usually we'll do something like this, right? We'll say product ID, int identity, not null. And then you might have, product name and varchar 20, not null. And then we might do, product price. And that is money. And we'll say constraint, PK, other products, primary key, product ID. And then we will usually throw a unique constraint in there. U product name, unique, and then product. This is usually what we'll do. And the reason I'm showing you what we'll do is I want to show you what happens when we do this. with indexes and then and clustered indexes, and then we'll make the table differently, just to show you that there are options out there that you can do. Let's put this on the file group products. Remember that file group we made? So I'm going to create this table in that file group. And then I'm going to run the entire thing. And it's done. Now I'm going to go to this other page here where I have that script from before that shows me where the tables, like what the index is and where it exists in the file group and what type. I've added a column that says what kind of index it is. So I'm going to run that. And now you'll see I have a PK other products, which is a clustered index. And then I have a unique constraint, which is a non-clustered index. So, interesting, right? So that's what happens when you build your table that way. Now let's demonstrate another way that you can build this table. Let me drop the table. Okay. And this time what we're going to do is we're going to make a primary key, and this primary key is going to be non-clustered. And we're going to make a non-clustered key on product name. So the name had to be unique anyway, right? Why not set it as primary key? That's great, but you don't want it to be a clustered index because names vary, right? You have no guarantees that you're going to insert these products A through Z. So that's going to make page fragmentation. So a better way to go about it is to make the non-clustered index like this. Let's run this. Okay, and then let's see what happened over here. So now we have PK other products. It's a non-clustered index. And now we have a index called null in the file group products, and it's a heap. This is where the actual data is physically stored. It's stored in the products file group, and it's not under any particular index. It's in what's called a heap. And what a heap is it sounds just like it is. Like think of a trash heap or a trash pile. It's just a big steaming pile of data. The data is actually stored in the order in which it's written. Okay, but there is no way to easily find any piece of data that you want because there's no key. Okay, it has no choice but to loop over every single page to find what you're looking for. That's the problem with not setting a primary key, is it makes it terribly inefficient when you're trying to locate the data within the database. So every table should have a clustered index, whether or not you want it to be primary key. So now we're finally going to learn how to separate that primary key from that clustered index. So I make my primary key, that's great, but now I could add it in here, but let's do an alter. Or let's add the index this way. Let's do go, and then let's say create clustered index. And let's call it IX clustered other products. IXC other products. And let's put that index on the table, other products. And the key that I'm going to use for the index is product ID. So what this says is it says, I would like to make this table, other products. And what I would like you to do is make sure that this is the primary key. So when I use foreign keys, it's going to use the product name for the foreign keys. But I'd like you to physically store it under the product ID. Okay, that's basically what I did here. Let's run this. Okay, all four of them ran. Let's go over here and see what we did. So now I have IXC other products in the products file group, and it's the clustered index. And then I have my primary key, and now that is a non-clustered index. So this is how you would split that table so that one value is used as the primary key and another value is used as the clustered index to break them apart. By default, what happens when you say primary key, it defaults to using clustered. You don't have to say clustered because by default it does clustered with primary key. Okay. Now to show you one last thing, you can't have more than one clustered index. As a matter of fact, if I copy this and paste it, and then say clustered index, products 2, and then other products, and then product ID and name. Let's use both columns. This is a completely separate index, right? You can see it's already yelling at me here. When I try to run this, it says, you can't create more than one clustered index. If I said non-clustered, I can create the index, right? So if I run this, it makes that index. And now if I run this again, I'll see I have 2 non-clustered indexes and a clustered index, okay? So we're going to get more into non-clustered indexes in a bit, but I wanted to first show you, basically now you understand that there's a difference between the primary key as a primary key constraint and the primary key as a clustered index, and you can split those and have one column serve one role and another column serve the other role. And there are times when this might make sense. You might want an email address to be the primary key, but you certainly don't want that to be the clustered index in the table. That's going to yield performance issues. Okay. All right, let's take a look at the non-clustered index. So the non-clustered index is a secondary index. It's used to improve the performance of a query. So this non-clustered index is like the index in the back of the book, whereas a clustered index is like the table of contents, right? The clustered index tells you how to get to a spot based on what's in the contents of the textbook. And the non-clustered index, which would be the equivalent of looking up a term in the back of the book. A particular term like primary key may appear on several pages, right? So there's no guarantees that the index key is unique, right? So that's sort of the idea behind a non-clustered index, or what's also called a secondary index. So you can create multiple non-clustered indexes on your table. You can make as many as you want. I don't know if there's a practical limitation in Microsoft SQL Server for that. The cost to you is extra space and extra inserts, because every index is maintained as like a shadow table, and that shadow table must be updated whenever the data in the primary table are updated. So there's a command create index. It looks like this. You say create, and then unique, and then or not index, and then the name of the index, and then on which table and which columns act as key, and then include these other columns in the index. That allows you to say what it is you're searching for within that index. So maybe you want to index by name, but you want to include their age. So that way, when you find Mike Fudge, you can get his age out of the index rather than having to use the index and not be able to use it to get the age because the age is in the table. And then, of course, you can save your indexes in a different file group if you want. So again, these columns are the index keys, and the index could be made unique. And the columns that you include are not part of the index key, but are included in the index. These are things you want to add to the index. Okay. When the columns are in the projection of the select statement, you get an index seek. And a seek is what we want. So here's a visual of an index. So let's suppose we have this table, and we want to create an index on the produce type, and then include the name. What we end up getting back is a shadow table like this that we don't see and we don't access. It's just there. And if I were to add in another row here, it would have to update this index. So here's what the index gives you. It'll give you a faster read. So here's my table again, right? Select name from produce where type fruit. Rather than using this table, it can use the index for that. And normally it would have to go, hey, are you a fruit? Yes, include you. Are you a fruit? No, don't include you. Are you a fruit? Yes, include you. Are you a fruit? Yes, include you. Are you a fruit? No, don't include you. All right, there's 3 fruits, print them out. When you build the index and you write this query, it'll say, hey, are you a fruit? Yes. Well, here are your 3 names. Boom, done. 1 row retrieved from the index, as opposed to scanning the rows to find what you want. That's where the index ends up being a better performance from a read standpoint. Where it's slower from a write standpoint is if you add a value to the table, like tomato, you do insert into produce, value 6, tomato, fruit. You then have to make sure the index gets updated as well. You don't update the index updates itself. But again, if you had 9 indexes on this table, it would have to do 10 writes. It would have to write to this table and then write to the 9 indexes. So that slows down the performance of the write operation. Same thing with deleting. If we delete this celery out of here, I have to delete it from here and then find it in the index and delete it. So you incur some penalties when you write and there's lots of indexes on a table, but you gain a lot of performance from the read operation. Let's discuss how to tune a query using an index. So it really comes down to scans and seeks and understanding that we want seeks over scans. So the worst performance thing you can do in a database is called a table scan. A table scan just asks each row if it needs to participate in the query. Do you need to participate? Do you need to participate? It's the worst case scenario. Because not only are we asking each row to participate, but we also may have pages out of order. So that's where a clustered index scan comes in. It's better than a table scan because at least we're using the primary key and at least the page ordering is going to be known. So that's better. Better than a clustered index scan is a clustered index seek. And in a seek, it's like reading the table of contents and then saying, go right here. And then we go right to the correct page to get the data we need. Better than a clustered index seek is an index scan. In an index scan, we scan the index row by row, but usually there's less rows in the index than there are in the underlying table, right? There's less types of fruit, or there's fruit and vegetable, that's it. But there could be, 200 fruits and vegetables listed in the table. So that helps improve the performance of the search because we're only searching through 2 rows. Are you a fruit or a vegetable? And then the best of all is the index seek, where you use that same index and you jump right to the value within the index. You use the table of contents on the index. So most queries have what's called a query plan tool, and the query plan tool will document how your query runs. And in the query plan, it will generally tell you how it's retrieving the data from the table. So down here, it says I'm doing a clustered index scan. So you have to know what that means and how it relates to this. So that's right here on the performance scale. So we could make this query better by trying to force an index seek or an index scan or a clustered index seek, a clustered index scan, or an index seek. That's how we can improve the performance of the query. So this is an example where I say select year name, average student GPA from students, group by year name. This query looks a little more complicated. It's a little harder to read. But in essence, it's still a clustered index scan. You'll see that I pull the data out of the table by its clustered index. Then I sort it. Why do I need to sort it? Because I'm grouping by student year name. So I have to put all the student year names together. And that takes 70%, 78% of the query is spent sorting that. Then I need to aggregate them by calculating the average over the ones I've grouped. Then I come up with a scalar, which says your average is 17 or whatever. And then I show it in the select. So that's basically how you read this query scan, but we can actually make this query perform better by eliminating this sort with a index. So how do you cover a query with an index? Basically, you want to look at your group by and your having and your where, and to some degree order by, but order by is usually what we do sort of last, and it's a cosmetic thing. It's not necessary to make the query work. And what we want to do is create an index key. The index key will be based on these values. and the columns that we include in the index are in the select line. So in the example from what you saw earlier, we would create a non-clustered index, students by year name, and then the key would be their year name, because that's what we're sorting by. And then we would include the values we wanted to show, like their first name, last name, and GPA. And in essence, that takes that first query we wrote, and it bumps it from an index scan before to a index seek. So now we've gotten so much better. Instead of doing a scan, we're doing a seek. We're jumping right to freshmen and grabbing the data we want. Much better performance. Now this says 100% and that says 100%, but that's the cost of that step. And remember, the entire query is always going to add up to 100%, right? But trust me, a seek is better than a scan, because a scan says, are you a freshman? 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 This one says, I've made a table of contents that says freshman, sophomore, junior, senior. You asked for a freshman, so I jump right to the correct page and give you all the data that you need. That's basically what's happening here with this where clause and this index seek. And again, it's because I made that index with a key of student year name. So let's check out the other query. The other query had this sort, and it did an index scan. Now it does a index scan, but it's a non-clustered index scan instead of a clustered index scan. So it's scanning the index that I made, IX students by year. It's using the index rather than using the table. And then in addition to that, the sort went away. And why did the sort go away? Because the index was created and the students were sorted by year, freshman, sophomore, junior, senior, right? And because of that, they come out in the proper order, and I don't have to spend any time sorting them to make the query work. So that's basically how you read a query plan. It works from the table end all the way to the output of the select statement, from one end to the other. And along the way, it's grabbing the data as you need it, and then it's applying these operations. Some of the operations are costly, some not so much. And basically where you can gain the most performance is not from these final steps, because they have to happen. I need the group, and I need the average. And there's no way to make that any better. But where you can improve the performance of the query is through the way it gets retrieved from the underlying table. And that goes back to, we want seeks over scans. We want to use non-clustered over clustered. All right, let's do a very quick demo of different query plans in Microsoft SQL Server's Azure Data Studio. Okay, I'm out here at Azure Data Studio, and I've got some code already written. I just want to walk you through how this explain feature up here works. So I run my query and I hit explain. Oh, I got to highlight the right one. And then I hit explain, and then you'll see that I have an index scan, right, over the clustered index scan over the primary key. And then I have a index seek over an, oh, I already have the index made. I got to get rid of that. That's not fair. Okay. All right, now I'll run it again. I have a clustered index seek. So I have a clustered index scan and a clustered index seek, and then it joins them together. And then after it joins them together, I see the output. And I can't really make this any better, because a join is a join is a join. All right. The only thing that I can improve in the query is what I'm doing with the data and how I'm sorting it before I prepare it for the join. All right. Let's take a look at this one down here. This one here has a window function right here on line 10. And it looks really complicated, but it's actually really easy to read. So you always start with the source, right? So over here, this is the source of the data, right? It's coming, this is a clustered index scan and a clustered index scan, one from major, one from students. Okay, it's the same thing we saw before. It needs to be sorted after I scan it, right? So why does it need to be sorted? Well, that's because I'm partitioning it by major name. So if you look on the sort, it'll tell you what it's ordering it by, major name down here. So that tells me the sort needs to happen. And then it's doing some segmentation. It's doing the partitioning. Then it's applying this lazy spool. So what it means when you do a table spool is it's now making this like the base table. And then that base table is used here and here. So here it's used to make an aggregate for GPA. And here it's used to join this table to the base table, and then that gets merged with the original table, and then what we have is the output you get. So I think I've demonstrated this in class before, where when you use a window function, it's actually like making a mini table that has an aggregate and then joining that on this as key, this major name as key. So that's basically what you're seeing out of this query plan. I clicked the wrong thing again. This query plan here. Bottom line here is all these things here, you can't do anything about them. Okay, that is what you asked for when you included a window function and when you included these columns up here, etc. So all you can really improve is the way the data comes out of the table and what happens to it along the way, right? So it gets sorted. So can I somehow eliminate this sort by using a non-clustered index? So down here, I'm going to make an index, and I'm going to use student major ID as the index. Now, why student major ID, right? Well, because in the partition, I'm partitioning this by student's major ID, right? Because I want to get the average by each major. Fine. And also, to do that, I need to sort them by their major ID, which is happening right here. Run that again. Right, sorting by their major ID here. Okay, major ID, student major ID ascending. So that seems like a really good candidate for an index key. So I create that index. There's my index key. Now I got to think about what columns need to be included. What I include here are the columns that are going to be showing in the output. First name, last name, major name, GPA. First name, last name, student GPA, and year name. But how come I don't have major name? Because that is not in the student's table. That's in another table. So you're kind of limited by what you can create an index on. So I'm going to make this index here. And let's show you how it improved the query. So the first query, the original query, now becomes a lot simpler. Right? Because I have an index scan and an index seek. Okay, and then this more complicated query that I did here with my window function. This has a index scan and an index seek, and I got rid of the sort because I no longer have to read the clustered index and then sort those major IDs in the right order. See, it's using the index that I made right here, IX students by student name or student major right here. So that tells me it's using my index. And that's really the point you want to see in query performance improvement is you want to replace those scans with seeks if you can. You want to replace those clustered index scans with non-clustered index scans if you can. And if you create an index and it doesn't get used, then obviously you didn't write the index correctly to improve the query. And the important thing to do when writing an index to improve the query is to include the proper columns. Now, I didn't need to include student year name, but I did. And here's why. Because if you make an index, you probably want that index to be used in a variety of different ways. And by making the index this way, I could actually have it improve the performance of this query here. Which also uses that that index right here. This second one here uses that index. So that's sort of the strategy that you want to adopt when you decide to make a query, improve a query through an index, is find out what that index key is going to be, sort that index key in the order it needs to be so that it satisfies maybe a group by or a partitioning, and then finally make sure you're including all of the columns in the index that would show in the output. That's it. So some general rules of thumb on indexing. When do you need to index? Like, do I really need to index a table that has like 25 rows in it? The answer to that is no, I don't. Okay. You should usually have, 6 figures worth of rows in your table before you think about doing an index. That doesn't mean you can't index before it reaches that mark, knowing that eventually it will, but there's really just no point in doing it until you know your data is going to be big enough. The searchable field should have a large, if a searchable field has a large number of null values, it makes sense to use an index. If the searchable field has a wide range of values, use an index. If the searchable field is queried frequently, use an index. Okay. The queries you retrieve are less than 2 to 4% of the table's rows. Great candidate for an index because you're constantly scanning the rows, but you only need certain pages out of the table. Okay. Avoid index when there's relatively few rows in the table. The column is not used for searching at all. The majority of the queries retrieve most of the data from the tables. These are usually good signs that it's not a good idea. If it's highly volatile, like it changes a lot, you might want to think about avoiding using an index in that case. So after a while, indexes will get fragmented. They will get kind of broken up as you do inserts and updates and deletes to the table. Those pages will not be optimal. The table clustered index might be fine, but all the other indexes that are using a different type of key, those are going to get out of whack relatively easily, and your indexes are going to become fragmented. You can reorganize your index, which physically moves the pages around, or you can just rebuild the index, which creates it from scratch. So alter index on table, reorganized, takes those pages and resequences all the pages so they're back in order. Alter index, rebuild, pretty much recreates the index. So let's suppose we have this fragmented index here. We can ask to reorganize the index, and what that's going to do is reorganize the pages. So page 1 comes down, page 3 now becomes page 2. Why? Because page 1, page 3, page 2. So it just reorganizes these pages, renames them, gets them in the right physical order within the file in the table space. When you have page fragmentation, you want to do a rebuild. Basically, this is going to say, all right, here's my current index. Let's just pretend like we're making that index from scratch and put everything in the right order in each page. So you end up rewriting that whole thing back out again. You can also specify a fill factor when you create an index on rebuild, and that allows you to leave space on each page, anticipating that there might be some additional inserts. So I can do, the first 3 on that page, next 3 on this page, last 3 on that page, and I would do that because I set a fill factor of 75%. So if there's 4 values per page, 75% would be 3 values. Okay. Let's do a quick demo of looking at index stats, and then from those stats doing a rebuild or reorganize of the index. Okay, I'm out here at Azure Data Studio again, and I have a demo table that I'm making that has, it's a table of items that has an item name. That's going to be the primary key. It's going to be clustered. Why clustered? Because I want to create some fragmentation here by like inserting some A's and then inserting some J's and then coming down here and inserting some B's. So everything's going to be out of order. And then I'm going to create a non-clustered index on the quantity. Okay, and quantity is a char because I'm going to make these, I need to make the table big, and you don't want to see me make a bunch of columns in here. So let me just make this table as is and show you something. So I make the table as is, and then in the notes of the slides, there's a query like this, and this query shows you the fragmentation of your indexes. So if I look through my indexes and I go down here to these items, I have a clustered index and a non-clustered index, and there's no fragmentation. And you might be saying, well, why the heck isn't there any fragmentation? You inserted those in all different order, Mike. The answer to that is they do not span more than one page. Okay, the data size is not big enough to span a page. So I need to pad these and make them bigger. So let's call this quantity, char 500. And let's make the item space waster column 2500. So now, I have 3,000 characters, 3,100 characters in every row. And a page is 8,000 characters. So this will now jump across several pages. Let me rerun it. And then let me go over here and rerun this. And now you'll see that the primary key, the clustered index, is 91% fragmented. And the secondary index on the item's quantity, that index is 80% fragmented. And this makes sense because I did not insert them into alphabetical order. And I did a foolish thing. I made the index before I inserted the data. If I make the index after I insert the data, it's not going to be fragmented, right? Because the data is going to be there and it's going to build the index over that. So let's use this data now as an example to show you how reorganize and rebuild work. All right, let's alter the index PK item name, right, which is this index up here, and on items, and let's reorganize it. So let's run that. Okay, we reorganize that index. Let's go back here and see how fragmented it is. Rerun this. Okay, now it's less fragmented. Okay, just from reorganizing. I think we need to rebuild it. So why does reorganization work so well? Because there's so few values per page, right? So I made my column size so large that there's only like 2 records on each page. So there's so few individual records on each page that reorganizing is enough to get the fragmentation down. If I rebuild, I don't know if it's going to do much better than that at this point. And maybe it will. No, see, still the same. So let's reorganize the items index. Let's do that. So alter index, and let's see what the name of that index was. IX items on items. Reorganize. Let's see how that improved it. Okay, still quite fragmented with a reorg, so let's do a rebuild. See how that handles things. Okay, so now that I've rebuilt, maybe let's try to reorganize again. Sometimes you need to do it after the rebuild. Let's see if I can get that down. Yeah, now it's down to 0. So reorganize, rebuild, it's like reconstructing that index from scratch all the way. And your mileage is going to vary on index rebuilds and reorganize based on, again, how many items are per page and how many pages you have. So I like this example a lot because you can come up here and tweak these numbers and change the number of items per page. Like if I want to put more items on a page, I can change this to 500. And then, that's going to add, about 8 items per page. And then you're going to see that probably a rebuild is going to be better than a reorganize. But that's basically the gist of dealing with index fragmentation, and more importantly, knowing how to discover in SQL whether or not your index is fragmented. This is the code to do it, which is quite tricky when you look at it. Okay, there's 2 more things. There's 2 more things to discuss. The Columnstore index. Okay, the Columnstore index is a means to queried the data across several different columns without having to make an index for each one. Rather than storing the data in rows, it actually repivots everything so that the data are stored in columns. That's why it's called a Columnstore index. And this is appropriate for tables that have a lot of columns in them where you want to leverage indexing across all these different columns. Okay. And it comes in clustered and non-clustered versions, and the data are compressed and cached into memory. So let's take a little tangent here and talk about what is a column store. So normally when you look at a table like this, how it's physically stored in a file is along what's called a row store. So if this were the file, you'd have, the row 1 would be stored US alpha 3000, and then next would be row 2, US beta, 1250. Then next in the file would be row 3, JP alpha 7000. And when you do an index seek, it jumps right to the proper row in the page. Okay. But if I wanted to retrieve all of the countries, I have to go to this row and then find US, then go to this row, then find US, then go to this row and find JP, then go to this row and find UK, right? So I have to go to each row, then go to each column within the file. A column store says, why not store things completely differently? Let's go over here and store them physically by their columns. So the first column is country, and then these are all of the rows in that column. And then the next column is product, and these are all the rows in the column. And then the last column is sales, and these are all the rows in the column. So this makes it easier for if you wanted to retrieve all of the countries, you just go to the country, row and then get all the columns. Okay. The row store is easier to add rows because they just get dropped here at the end, right? The column store is easier to retrieve a column. So you are making a choice. Do I want to improve the performance of retrieving the data in any of these columns? Or do I want to improve the performance of being able to add or update rows? Because if I were to update this row right here, US beta 1250, and let's suppose I want to make it US alpha 4000, I actually need to do 2 updates to do that row. I need to say US is the second one, and then I need to go to the second product and change that to alpha, and then go to the second sales and change that to 2000. So I actually have to do 1 read and 2 writes just to do an update. Whereas over here, I would find the row, 1 read, and then I would do the update to that row, 1 write. Okay. So that's where the disadvantage of the column store comes into play. So a column store index can be created as follows. Create, clustered or non-clustered column store index on table. And then each column that you want to participate in the column store index, you include here. These are not key columns. They are just the names of the columns that are going to participate in the index. Okay. And this is a fantastic way to ad hoc query a lot of columns from a table where you do not know what you want to improve the performance of, and you're not super concerned about the fact that it's going to degrade the writes on that table. So imagine a table with a lot of columns, and you want to be able to index all of those columns. This is a great way to do it. Let's quickly do a demo. Okay, I'm out here in Azure Data Studio, and we're using the FudgeMart database now. And I have this query here, which gives me a count of orders by the service used to ship them. Okay, pretty common. And if I look at this, I might want to improve the performance of this query because it's already using my column store index because I didn't drop it. Whoops. Hold on. All right, that looks better. I got rid of the column store index I created before. So now it's just doing a regular index scan. Okay. And you might say, well, I would like to turn this into a non-clustered index scan, and I would write this index here. That it would improve this query, but it would not improve this query where I'm asking for a different. I'm asking, this one is by customer ID, or this one here is by credit card. So if I want to improve the performance of all of the columns in FM orders, I do a select are from FM orders, and I want to improve the performance of all of these columns, then I should try a column store index, because what I can do is I can create this column store index and specify the columns I would want to include in it. And normally we'd have more than 3. You'd have a lot because you want to really leverage the column store index. And now this column store index is covered by, let me drop it first. And let me recreate it. Okay. Now this column store index covers any queries that use this, or this in it. So I'll show you. So this one says, I'm using a column store index. And then this one says, I'm using a column store index too. And even one where you specify a combination, like I want to get a count of credit cards from orders, but I want to filter on a customer ID, even this is going to use that column store index because the column store index covers every single column that you specified. Column store index. Every single column that you specified in that on clause. Okay? So it works a little differently than a regular index. There is no index key. There are only columns. And it rewrites the data so that each column is now a row, and the values in that column now make up the rows within that individual column row. And when you store the data this way, it performs better for queries, by far better than any other kind of index, but it is a very slow update operation. And you have to be sort of cautious of that and consider that. So this makes sense for data that you know is not going to change anymore, but needs to be queried rather quickly. Okay, last on the docket for today are index views. So index views are an easy way to improve the performance of a view. What this does, in essence, is allow you to take that view output and treat it like a shadow table, if you will. It's also called a materialized view in other database management systems. And basically what will happen is we'll take that view output and then create an index, a clustered index on it. And this will build, if you will, a copy of the view output so that we have an automatically updatable yet shadow copy of whatever was in the view. And this will greatly improve the performance of querying the view because it doesn't need to go back and query the underlying table anymore. So what the requirements for doing this is that you need to use with schema binding, which means that you're going to create this view and all of the columns that are in there are going to be accessible. Think about when you make a table, you need to have all the columns, right? So same thing sort of happens with a view. The view must be deterministic. It can't have some kind of random generation in it. Every time you run the view, if it has a certain filter on it, it should always produce the same output until the underlying data in the table changes. It should not be based on some kind of time variance or things like that. All the columns must be specified. You can't have select star in the view. And you must schema qualify the table. So the base schema in Microsoft SQL Server is DBO. You must include that in front of the table names in order for the schema binding to work. And the clustered index works like a primary key. So let's give this an example. This will be our final example of the day. All right, I'm back here in Azure Data Studio, and I'm in TinyU, and I have this view students that I made, and it is student ID, student first name, student last name, GPA year, major name from students, joining to majors, right? So if I run it, it's pretty simple. Just gives you a view of all the students and their majors, right? And the name of their major. So I might want to make this into a materialized view or an indexed view. And what that would give me in essence is this would be a table of data. It would be a copy of the original data. But if I ever changed a name, like if I changed validation's GPA to 3.7, it would automatically refresh that in the view as well. So it's going to write the data twice to the regular table and also to the index view. And it does that automatically for me. And again, why I'd want to do this is maybe the query that creates this view is very complicated. In this case, it's not, but it could be very complicated. And you want to take the output of that complicated query and store it as a table to improve the performance of people that are actually querying the view. So here's how you index a view. You add with schema binding, and then you need to put DBO in front of the objects you're querying. And that will create a schema bound view. Oh, I got to get go in there. And then from here, you can actually make an index, a clustered index on that view. Okay, and then you can query the view and it looks the same. Now, this doesn't really help us because we don't see the query plan, right? So let me drop the index. Okay, and then let's run this as a query plan. And you can see it's joining two tables together and then producing the output. Now let's create this index. And then let's look at the query plan. It's not joining two tables together anymore, folks. It's just reading from a clustered index. So again, imagine this view, this code here in the select is really complicated. It's got a window function, it's got a multi-table join, maybe it's got a with statement and a union query. It could be nuts. That's a great candidate for building out a schema-bound view and then adding a clustered index to it. Because that way, when you go to query the view later on, the retrieval process has been trivialized, and you don't have to worry about the taxing amount of effort that goes into running this query here. So it's yet another performance trick. Okay, let's sum up with some physical performance tricks. So first of all, if your server has more than one disk, it might make good sense to make a file per disk in the same file group to spread your I/O out over the disks. If your server has faster disks, it might make sense to take tables that you know get a lot of reads and writes and store them on the more expensive yet faster disk in order to improve the performance of access to those tables. Don't store the database files on the same partition as the operating system itself, because your operating system has reads and writes and I/O that it's doing, and so do your data files, and it's a good idea to try to keep those independent. Okay? And the last tip is take the data that grows fast, like maybe your associative entities or time series data, and definitely put those in their own file group. That way that file group can grow and grow and grow independently of all the other tables that are in the primary file group or the default file group that may not grow as often. So let's sum up what we did. This was a very long lesson in performance. So the physical model is an implementation of the logical model in a DBMS. The SQL Server physical data model has servers, instances, databases, file groups, files, and pages. And indexing allows us to improve the query performance at the expense of the write performance. So reads are faster, writes are slower. It doesn't matter whether it's a clustered index, a non-clustered index, or a column store index, or an index on a view. In every case, what we're doing is we're increasing the number of writes, but we're improving the performance of the reads. And the balance there is one that you have to strike in order to produce the best performance for your particular database application. Column store indexes store table data in columns, and this gives you a tremendous boost in retrieval when there are multiple columns in the table and you know you're going to be querying by different values in those columns. And views can be indexed, and an index view greatly improves performance, especially when the query is complicated, involves many table joins or some kind of set operator. Those are great candidates for an indexed view.